So there's a lot of different applications for filters. They have a variety of uses. Probably one of the most common is maybe removing undesired frequency content. Maybe like if we look at this signal here, we could say maybe there's some noise on top of the signal that we're measuring. So we could use a filter to remove that noise. So signal cleanup is a common filter application. Another could be signal analysis. Maybe you're familiar with this. This is the A weighting curve. It's used on our microphone data to kind of introduce characteristics that simulate the human hearing into a microphone recording. So we can use this filter to alter the frequency content of a time signal, or so by reducing certain frequencies and maybe even amplifying others. Now, there's different ways we can use filters because there's different filter types. Like the one we just saw, that was a high pass filter, right? We're attenuating frequencies up to a certain point, and then we're passing them through. There's a low pass frequency filter, does the same thing, but an opposite. We would be passing certain frequencies up to a point, and then we start to attenuate them. And then there's a band pass, where we are passing just the frequencies in a particular range, or a band stop, where we are attenuating the frequencies in a certain frequency band. So moving into the next section, it's always hard to ask questions over these webinars, but
infinite rigatoni. I'm going for that.
You're going for rigatoni? Okay, you know what? That's a good choice.
I regret it. I'm moving to regret. I'm on immediate regret now.
Yeah, you might regret that decision. So what does the IR in FIR and IIR mean? Well, it means impulse response. And the reason is that term refers to the appearance of the filter in the time domain. A response is really short in the time domain, like an impulse or impact, has a broad frequency response. Well, obviously the inverse would be true too. Filters typically have a broad response in the frequency domain. So in the time domain, this represented more as an impulse. And many times we define filters when we talk about the characteristics about the filter in the frequency domain, but they really do their work in the time domain. So when we talk about defining a filter, I mean like talking about the pass band, the area where the filter may not be attenuating anything. This transition band, where we can see how sharp the filter may be, depending how wide this region is and how much attenuation we're getting. Then there's the band stop. And when we look at the band pass and the band stop, another thing we would define is the ripple.
Is it possible to have zero ripple, Charles? Or do we always have to have ripple?
It depends a bit on the window function. Some window functions are better than others when it comes to the pass band, for sure.
So we can get some pretty flat frequency responses, I assume.
Yeah,
doesn't always happen.
And that's what you want in the portion that you are in the pass band. You don't want to affect that signal with any of this ripple by amplifying it. So this is the FIR filter equation. This equation has basically three components, we should say. So there is the input time history here, and this lowercase n basically represents the total number of data points in the time history. And then there's the filter, represented by this A here label, and the uppercase N relates to what we call the filter order, right? And we also call it taps too. It can be referred to as taps, and we'll talk about that shortly. And then there's the output time history, right? So those are the three components: the input, the filter, and the output signal. We were just talking about how that cap in represented what we call the filter order. When we talk about order, we're talking about the number of points that make up that filter. And if we say a low order or a low number of points, we have a more gradual filter. It's not as sharp, right? So this is a 5-term filter. And if we look at one that was a 10-term filter, we can see we have many more points here, double. And when we have higher order, more points, we get a sharper filter.
If you go back and forth, Charles, can I watch that effect? Ooh, 5. Oh, Yeah, that's much sharper.
You like that? Why don't we look at a demo actually too, Pete, of this filter order? You got one for us?
Sure. Yeah, so the data you might see looks like in red, a bunch of random data. Would that be right? And then in green, you see a sine wave.
Yes.
Okay. I summed these together using our software to make a sine wave plus some random data. And I thought maybe a nice little challenge would be to use the filter to kind of see if I can separate this data again. So I got the time history here. And when you go into this FX button here in our time signal calculator of Test Lab, and you click on conditioning, whole bunch of filter choices. So a lot of the ones that you talked about, Charles, a band pass, a band stop, arbitrary shaped filter, high pass, low pass, order, etc. And I got one of those filters defined here, and there's actually a show button. Depending how you defined it, you can see the filter shape. So this is showing me an FIR filter, Kaiser filter. It's 20th order, and the cutoff is set to 1,000 hertz. So I have a low pass 1,000 hertz filter, order 20, whatever that means. I'll hit OK here, and I'm going to hit calculate here to see that filter. So I get a new trace, and I click on it. I click on this button here. Normally they would be separate like this when you display them, but if you know the secret button with the 6 squares, you can look at and overlay them. Did I do a good job filtering that, Charles?
It's a good start.
That's a good start. I don't think I hardly did nothing at all. You're so nice, but
I was trying to be
you can
kind.
say it's a lousy start, right? So you mentioned a few things. Well, one thing is this sine wave is about 2 hertz, and I have my frequency cutoff set to 1,000. So maybe I'll take that down to 100 hertz, okay, and then see if that improves. Oh yeah, I got rid of a little bit more noise there. Maybe I'll go even further. Let's say 5 hertz or something, and hit calculate. No, not much of an improvement. Now, what was that thing you were saying about order, Charles?
Yeah, the sharper the filter, the higher the order.
Yeah, so here I have an order, and I could increase it by a factor of 10. And if I hit show, that looks just, well, for lack of a better word, looks a little bit sharper, Charles. So I got 20th order, then I increase that by a factor of 10, and well, that's really starting to do some filtering. So I'll hit OK here, and then I'll hit calculate selected. Oh, now I'm starting to see something that looks like the sine wave, Charles.
Oh, that's moving the ball. Yeah.
Yeah. Now we can move the ball a lot. I could even go up by another factor of 10 here. Show that. And that's even sharper than it was when it was 200. So with 200, it looked like that. With 2,000 as my order, getting there. I'll hit calculate. Whoa, and it looks like I managed to retrieve that sine wave pretty nicely by changing the order. And you can see it is going from, the original one was minus 0.4 to 0.4. So we're actually getting pretty close there. So that is an example of filter order, Charles. Is that kind of what you were hoping to see?
That's exactly what I was hoping to see, Pete. Thanks a lot. So I have another slide here, just basically summing up what Pete was talking about there. When it comes to defining these FIR filters, the higher order, sharper the filter. And we can see that from 10 to 200, we can see quite a bit difference.